Welcome everyone. Thanks for coming to today's seminar. It is great we have Dr. Rian Hall. I think he will become doctor very soon. He will attend the graduation ceremony in this month. Rian is just a recent PhD graduate from SPREE. In his thesis, he just developed a efficient computational framework for characterizing the semiconductor materials. His research interests are broad but are driven by a general goal by transferring the theory into applications. He has a very interesting career background. He used to be a radio frequency and analog electronics engineering, work for the space industry, and also work for the atomic quantum computational laser control. Today he will talk about why we should care about the computational material discovery. Let's welcome Rian. The stage is yours.
Well, thank you everyone for being here. I guess my goal by the end of the seminar is to convince everyone that there's a lot of value to be gained from performing computational material discovery. But beyond that, during my thesis, I learned that it's not just for discovering new materials, but also understanding and appreciating some of the underlying physics. These sort of high-throughput computational studies can be leveraged to learn a lot more about material systems in general. And in my case, I wanted to present on a case study of modeling impact ionization, a high-field scattering mechanism. A lot of this work is, founded from my PhD, and so I just wanted to thank and acknowledge my two academic supervisors who are here, Dr. Fiac Ruggiero from SPREE and Professor Francois Ladouceur from Electrical Engineering and Telecommunications, and also an industry partner who gave really valuable insights throughout the thesis, Norbert Kraus from Solana. So I thought I'd start by describing exactly what impact ionization is. Here we have a fictitious band structure. There's a valence and conduction band represented in black lines, and the slope here shows some applied electric field. We have an electron occupying each of these bands, and in the presence of this high field, this conduction band electron could gain sufficient energy to ionize the bound carrier across the band gap, generating an electron hole pair. If this electric field persists, these subsequently generated carriers can be further accelerated by this electric field, generating more electron hole pairs. When this process runs away in this manner, it's known as avalanche breakdown. And we normally think of avalanche breakdown as being detrimental to a lot of devices. It leads to degradation and failure. It limits the maximum voltage or electric field that we can operate power electronic devices at. It reduces the efficiency in optoelectronics, and it limits our ability to miniaturize modern CMOS devices. But impact ionization can also be quite useful. Here we have the same fictitious band structure again, only this time, let's say, a photon with just the right energy comes in and ionizes our conduction band electron to a higher energy state. Now it can impact ionize this bound carrier across the band gap, generating that same electron hole pair, and in the presence of an electric field, this process can lead to an avalanche breakdown that generates a large current in response to, say, a single photon. This exact mechanism is exploited in devices like avalanche photodiodes, or APDs. It can also be used for microwave or RF generation in devices like impatch diodes. And it's commonly seen as a common mechanism in high voltage protection devices like Zener diodes and electrostatic discharge protection diodes. But the motivation for my PhD didn't come from these existing applications. In fact, when Solana initially proposed this project, they were interested in UV light emission. And if you look at this graph here, it shows the external quantum efficiency of conventional LEDs as a function of the emission wavelength. And you'll notice, particularly in the UV regime, this efficiency, this EQE, dropped down quite significantly. Now, all of these devices use very, very similar architecture. Functionally, they're a PIN diode or a PN heterojunction with an N-type contact for injecting electrons and a P-type contact for injecting holes. In the middle, our recombination layer is typically constructed of a heterojunction forming a multiple quantum well in the case of LEDs. So why do these UV devices perform so poorly? Well, the external quantum efficiency can be thought of as a product of our injection efficiency, our internal quantum efficiency, and our extraction efficiency. Now, the reason UV LEDs perform so badly is because we're extremely constrained in the available material systems that we can use. And this comes down to that preconceived notion of the device architecture we use, namely this p-n heterojunction. And the material system that's conventionally adopted is aluminium gallium nitride, or AlGaN. And it has quite high threading dislocation density, which limits its IQE. It also has split modes of polarization, which limit the maximum extraction efficiency. And so this is the reason we see this large drop-off as we move towards 200 nanometers. But Solana had this idea of, well, why do we use a p-n heterojunction as our LED structure? What if we looked at the way we inject carriers? Could we unlock new material systems and avoid issues with the IQE and the extraction efficiency by looking at different carrier injection mechanisms? And their idea was to use impact ionization. The challenge here was, can we achieve efficient carrier injection in wide and ultra-wide bandgap semiconductors? And their proposed solution was to generate these charge carriers using an impact ionization generation scheme. Going back to our fictitious band structure again, the way this is applied, we have, again, a conduction band electron accelerated by an applied electric field. It generates an electron hole pair via impact ionization. Perhaps some number of collisions occur in an avalanche scheme. But if we can find some way to relax this applied electric field, we can allow for radiative recombination and hence light emission. The way Solana achieved this is through a spatial device. We have a sort of simplified structure shown here with two N-type contacts. And this is important. We've mitigated the need for a P-type contact in this material. In this case, the top three layers, the impact ionization layer and this charge/chirp layer, form or functionally act like a P-type contact. The way this works is we inject an electron into the bottom N-type contact here. It travels through our recombination layer into the charge layer where it's accelerated to sufficient energies to generate an impact ionization event in the impact ionization layer. The subsequent electrons flow out of the device, but the generated hole flows in the opposite direction where it can recombine with another electron inside this recombination layer, leading to light emission without the need for a P-type contact. And this is important, as I said, because the need for a P-type contact in wide and ultra-wide bandgap semiconductors has severely limited our material selection. So the question Solana posed to me is, can we generate new materials, or can we investigate new materials and their feasibility to achieve efficient carrier injection using this impact ionization scheme? And so the goal of my research is, in general, can we identify materials with favorable impact ionization properties for devices? And my approach was to develop a high-throughput framework for computing the impact ionization properties of materials. High throughput is a keyword here, and it's important because it prohibits experimental characterization as a valid approach. It also prohibits computational methods that are intractable to large-scale analyses. And so I started with this problem and started to look at how we model impact ionization and what the limitations are on it. So impact ionization can be modeled in a multi-scale modeling scheme all the way from the microscopic scale right up to the macroscopic scale. At the microscopic end, we have electronic structure calculations like density functional theory, from which we can derive important microscopic properties like the impact ionization scattering rate. This scattering rate tells us the number of carriers generated per unit time as a function of the initiating carrier's quantum state. And it has an associated impact ionization threshold. On the macroscopic end, we have properties we care a lot more about for engineering semiconductor devices, namely the impact ionization coefficients. These describe the number of carriers generated per unit distance traveled by a carrier as a function of an applied electric field. And from this, we can access experimentally observable parameters like the multiplication factor, or in the case of power electronic devices, the avalanche voltage breakdown fields, etc. So how do we bridge this gap from the microscopic to the macroscopic? Well, conventional computational methods leverage stochastic methods like Monte Carlo techniques to infer information about the impact ionization coefficients from these more fundamental properties. But these are computationally intractable. And so my research goal was, can we learn something about these experimentally accessible properties just from these microscopic properties alone and build an efficient computational scheme for identifying new material candidates? I'll delve into a little bit more of the theory here, but it shouldn't be too important to the kind of message of this talk. But generally speaking, impact ionization scattering, the scattering rate of the terms of the number of carriers generated per unit time, has this sort of functional form that looks like this, where as the energy of the initiating carrier increases, so does the scattering rate. And the important parameters of this curve are the threshold energy, that's the minimum energy an initiating carrier can have and undergo an impact ionization scattering event. And we also care about how quickly the scattering rate increases beyond this threshold. The most rigorous way to model this comes from first-order perturbation theory, where we use Fermi's golden rule to describe the transition rate from a set of initial states to a set of final states. This formula here looks a little bit intimidating, but effectively what it says is that the transition from an initial state in K1, impact ionizing a state in state 2 to these two post-collision states can be described as a product of a matrix element, which describes their interaction probability, multiplied by their density of final states, which is captured by this direct delta expression here. And this process is subject to two conservation criteria. Here we can very clearly see that the energy conservation criteria is described, and if we write K2 in terms of K1, K3, and K4, we have the momentum conservation constraint as well. Practically, we want some energy averaged transition rate. We don't want to see what an individual scattering probability looks like for some random set of carriers. And so we have to integrate this complex function over all possible combinations of post-collision states. And that leads to this very gnarly six-dimensional integral with a composition of a direct delta. Again, we're getting into computationally intractable territory. And this is without even exploring the matrix elements, which in themselves are a very challenging problem to solve. And the integral doesn't stop there. If we want the energy averaged rate, now we have to integrate over all of the constant energy isosurfaces and figure out for a given energy what's the average rate of impact ionization. I didn't want to do this, not only because it was hard, although that was very convenient, but it's computationally prohibitive to these high throughput applications. And so, luckily for me, the more useful output of these sort of studies is this Keldysh model formalism for the impact ionization scattering rate. And effectively, it just says that this energy average scattering rate can be described by this simple function where we have an exponent term alpha and a threshold energy ETH and some sort of average matrix element described by P. Typically, these parameters are fitted to the outputs of these more rigorous studies using Monte Carlo methods from Fermi's golden rule. But as I said, there's three critical parameters of interest: the threshold energy for impact ionization, how quickly this impact ionization scattering rate increases, and the average matrix element of the scattering rate. And each of these three parameters formed a pivotal chapter in my thesis. We're going to start with the impact ionization thresholds. So to compute the impact ionization thresholds, here we have again a fictitious band structure, and we have an electron here denoted in state 1 with some energy. When an impact ionization event occurs, this initiating carrier ionizes the bound carrier in state 2 across the band gap to a new state, which we'll call 4, and itself must lose that energy relaxing to state 3. As I mentioned before in Fermi's golden rule, we know there are two conservation criteria that this scattering mechanism must satisfy. One is that the total energy must be conserved, and the other is that the total momentum must be conserved. And so taking these two conservation criteria, we can solve for the minimum energy that this initiating carrier can have if we know information about the electronic band structure, and then define the impact ionization threshold. It turns out it's rather convenient to solve this minimization problem in two steps. First, we kind of say, well, let this initiating carrier come from any state. It's not bound to the band structure, and we're just going to minimize the total energy of the post-collision states and the impacted carrier. That will give us this curve that describes the minimum energy as a function of an initiating carrier's momentum. And then from the intersection of that curve with the band structure, we can find the true impact ionization threshold. This next figure hopefully makes that a little bit clearer. But before we get on to that, conventionally, this impact ionization threshold in these sort of experimentally accessible simulation environments is approximated by this rule called the 3-to-2 band gap rule. And I guess the main output of my first chapter here was to show that this is a really poor approximation. It comes from an assumption that the effective masses are equal in the conduction and valence band, and inherently that the initiating carrier comes from one of those bands. And if we make those assumptions, it turns out that we can say the threshold is just 1.5 times the band gap of the material. So back to the figure that hopefully makes this minimization strategy a little bit clearer. Here we show the band structure for gallium nitride with a band gap of 3.4 electron volts. And superimposed on it is the blue curve showing the minimum energy an electron would need to have as a function of its momentum in order to satisfy the energy and momentum conservation constraints, and red is the same for holes. Where this curve intersects the band structure, we have an impact ionization threshold. In fact, the threshold is the lowest energy intersection with this band structure. All of these higher order interception points are important, but we'll kind of get back to those a little bit later on. So I took this minimization algorithm and I wanted to leverage this database called the Materials Project in order to perform these high throughput analyses. So the Materials Project database, it contains several 100,000 density functional theory calculated electronic band structures. And we use that information and we extract from it the band structures, crystallographic information, and things like the phonon dispersion relation. We then perform our minimization algorithm to extract the thresholds of impact ionization, including a few pre-processing steps. And finally, we have our outputs, which we can recontribute to the academic literature or directly to the database through their API. And so what did those results look like? Well, this next slide shows the impact ionization threshold energy versus band gap for electrons on the left and for hole-initiated thresholds on the right. In the legend there are two different types of threshold. There's one where this minimum energy curve does intersect the band structure, and that's given the circle marker, and there's another one where it does not, given the triangular marker. I'll explain a little bit more about that in a minute. But the other thing that we can see here is I've also shown in the dashed line the 3-to-2 band gap rule, and the solid black line just assuming the threshold equals the band structure. The band gap. We can very, very clearly see the 3-to-2 band gap rule, particularly for wide and ultra-wide band gap semiconductors, becomes quite erroneous, a very poor approximation. And the little zoomed in section there shows that even at very, very narrow band gaps, seldom is the 3-to-2 band gap rule actually a viable approximation. So why is this the case? Well, like I said before, the 3-to-2 band gap rule assumes that impact ionization, firstly, the carriers have to come from these first conduction and first valence bands, and that those bands have to have equal effective masses. And so for that to be true, the energy conservation criteria alone tells us that therefore the intraband energy range of that first band must be at least the band gap. The idea being here that in order for a carrier to undergo impact ionization, it has to be able to lose at least a band gap's worth of energy and remain in the conduction band. Therefore, if it's to come from the first conduction band, that conduction band has to have an energy range that is at least a band gap's worth. These plots on the right show the intraband energy range versus the band gap for the materials that we explored in this high throughput analysis. And if we project onto this a curve that shows when the intraband energy range is actually larger than the band gap, we can see that it actually excludes most of these materials. Another way of looking at it, these same figures again show the intraband energy range, but now on the right axis we show the proportion of materials at a given energy that satisfy this criteria that the intraband energy range is greater than the band gap. And we can see once we go above sort of 1.5 to 2 electron volts, in both cases, fewer than 50% of the materials satisfy that criteria. And so this kind of gives us an indication of when might the 3-to-2 band gap rule be applicable. And beyond this point, it can't be valid at all. I mentioned before there were kind of two different types of thresholds we discovered, and here's an example of the second kind using holes in aluminium nitride. So if you turn your attention to the bottom of this curve, you'll see that for all energies across this minimum energy required for a hole to initiate impact ionization, the density of states is 0. So there's no way that we have an intersection between the minimum energy and the band structure itself. So what's the impact ionization threshold in this case? Well, we assume then that it must come from the next available energy state. And so this threshold in the case of aluminium nitride gets pushed up to quite a high value. And this actually has really important implications for materials. We can look at something like the electron-hole threshold ratio. Why might this be important? Well, we talked about APDs at the start. One of the really important properties for APDs is that you have high asymmetry between the electron and hole initiating impact ionization coefficients. And this is because the excess noise factor depends quite heavily on this ratio K. It turns out that the impact ionization coefficients are quite strongly related to their thresholds, and so we can say that K is approximately has an inverse exponential dependence on the difference between the hole and electron-initiated threshold. So if we can find materials with a really large difference between their electron and hole-initiated thresholds, they might be really good material candidates for avalanche photodiodes. And so we can compute this from our threshold results as before. In this plot, I've replaced the x-axis. Instead of showing the band gap, I've showed the corresponding wavelength. And the y-axis there is the difference between the hole initiating threshold and the electron initiating threshold. We can see, particularly at these really short wavelengths, in the deep ultraviolet regime, there's quite a few materials with a lot of asymmetry. For those interested in specific materials, I've also got some tabulated data that shows some of these potential candidates for APDs. And if you want to have a detailed look, go to the recording or read my thesis. So this first chapter, we kind of solved the question of what the impact ionization threshold looks like. And we can use that to already perform some really meaningful material discovery. We can identify candidates for APDs, and we can delineate the importance of the threshold in terms of debunking the 3-to-2 band gap rule. So in the second chapter, I wanted to explore how quickly this impact ionization scattering rate increases as a function of the electrons or hole's energy. And to do this, we can actually leverage some of the information that we generated in the first chapter. One of the things you'll notice about this minimum energy curve is it shows a lot of K-space anisotropy. It changes as a function of the applied momentum. And in the 70s, another author, Sano, had this idea that this anisotropy in the minimum energy required for impact ionization is largely responsible for the onset of impact ionization about the threshold. The idea being that this K-space anisotropy really comes from the momentum conservation constraint. And at threshold, we know momentum is perfectly conserved, but we're very sensitive to changes in momentum close to the threshold, where the phase space for our scattering rate is very, very small. And so he said, well, if we have an electron above a threshold, it definitely will impact ionize. This is an approximation. And if we have one below the threshold, then it won't. And we can write that as a Heaviside step function. We could say, well, if our energy in our band is greater than our minimum energy required for impact ionization, the probability of impact ionization is 1. Otherwise, it's 0. And with that, we can then integrate it over these closed energy isosurfaces to kind of get the energy averaged probability of impact ionization. In order to solve this on a high throughput scale, I had a lot of fun developing some new methods for the simulation. This integral, while it's only in 3 dimensions, it still involves that rather challenging composition of a function with a Dirac delta. And so I leveraged methods that were used in computer vision to solve this integral in a computationally tractable manner. Namely, I used an algorithm called the marching cubes algorithm to extract these constant energy isosurfaces and their normals and compute this integral. And so the workflow was to interpolate our thresholds in K-space, extract these constant energy isosurfaces, and then compute the corresponding probability integral, which we can see on the right, for gallium nitride. Here are some of the results compared against the author's original work and some other work that was replicated later on. At the time when this work was done, the value of it wasn't fully appreciated. I think Sano's idea was that it would be a stand-in for the scattering rate itself, but that was very quickly debunked in subsequent literature. Some other authors looked into it as an interesting metric, but there was no really useful result to derive from that. The work initially performed here was just to validate that our integration method works well, and we can see, at least in this case for silicon and gallium arsenide, we have similar probability curves to those proposed by the original author and subsequent authors, with a bit of a big difference in the case of silicon, but this was addressed also by Harrison al. In their subsequent follow-up. But the real value in the impact ionization probability isn't from this curve alone. This doesn't really tell us much. It kind of gives us an indication of the onset of impact ionization close to the threshold. But again, we can't use it in Monte Carlo simulations to kind of derive these important experimentally observable properties. Looking at gallium nitride and aluminium nitride, though, we can learn something, at least from these curves alone. I think one of the most interesting results I got from these wide bandgap semiconductors is that sometimes this probability curve is not monotonic. And this was a frustration for me during the PhD, as I was consistently predicting the threshold energy for aluminium nitride to be virtually equal to its bandgap. But everyone else that was doing these comprehensive calculation using Fermi's golden rule, they were finding the threshold energy to actually be up around here, around 6.6 electron volts. And this is because while we can find a threshold here, i.e. a point where the energy and momentum is perfectly conserved, the corresponding phase space could still be very small. And we don't know because in this probability assumption, we say, well, if we're above the threshold, impact ionization definitely occurs. But we're not guaranteed to satisfy those two constraints. But from this curve here, we can at least extract interesting inflection points where the true experimentally accessible threshold might actually lie. And so I took this a little bit further and thought there's got to be something else we can do with these probability curves. Going back to Fermi's golden rule, there's an approximation that was introduced late in the 60s where we kind of dropped the requirement that momentum needs to be conserved. This is known as Kaynes random K approximation. And it kind of turns out quite nicely that you can then represent the energy average scattering rate as simply an integral of the single particle density of states. The problem with this approximation is that then your threshold energy just always ends up being the bandgap because you're not constrained by the criteria to conserve momentum. But our probability curves do take into account the effect of this anisotropy close to threshold. So what if we took Kaynes random K approximation and we just multiplied it by a probability curve? And I define this term the probability moderated random K approximation, and it kind of corrects the near threshold behavior of Kaynes random K approximation. And this is quite good because looking at Kaynes rate, we know at high energies it converges to the true scattering rate of the material. And it's the near threshold behavior that's really important for how devices actually operate. And just to prove that this is useful, I looked at this for silicon, gallium nitride, and aluminium nitride in detail, where there was data I could compare against in the literature. And you can see that the dotted lines there show the random K approximation, and the solid lines show the results with the probability moderated random K approximation. The markers there show the data from the literature derived using the full Fermi's golden rule calculations. You can see we see remarkable agreement between the PMRKA and these full band methods with very little computational overhead. And this is true for silicon, for gallium nitride, and also for aluminium nitride. And so the output of the second chapter of my thesis, to kind of discover how this onset of impact ionization occurs close to the threshold, I felt like I achieved that, and certainly my examiners agree. The last thesis in my chapter was looking at this sort of averaged matrix element. And this kind of gives us the y-scale of our probability curve, at least on the log scale. It shifts it up and down. This is really important because if we want to do some sort of downstream Monte Carlo analysis, the absolute value of our scattering rate is absolutely critical. So far, we've used something called the constant matrix element approximation. We just assume that the matrix element is some constant value over all energies. If we wanted to comprehensively model the matrix elements, we have to calculate these very cumbersome overlap integrals between the pre- and post-collision states. And in between that overlap integral is this Coulomb potential that describes how strongly coupled these states are. If you look at the Coulomb potential and the denominator there is a dielectric function of momentum and wave, it's getting computationally intractable very, very quickly. So the constant matrix element approximation says, let's not do that. Let's just say it's just a constant value and we'll tune it to experimentally accessible data. And this has proved to be actually quite good for indirect bandgap semiconductors, but unfortunately it's quite a poor approximation for direct bandgap semiconductors, especially wide and ultra-wide bandgap materials. And so I thought maybe there's a way we can introduce some of the momentum dependence of these matrix elements without going through this comprehensive overlap integral calculation. We kind of look at the Coulomb potential here. We can see in the denominator we have this Q squared sort of term, and this is the momentum exchanged between the initial and final states. And so I thought maybe the matrix elements are strongly coupled to some functional dependence on the average momentum exchanged between the carriers. And when I looked into this, I was quite surprised about how good this exactly was. Here are some of the results. On the left, we show the average momentum exchanged versus the initiating carrier's energy in gallium nitride. And on the right, we have a functional form that's a 1 on q to the 4 dependence. So that's that q squared again, because in a scattering rate calculation, we use the squared magnitude of the matrix elements. So is this a good approximation? Well, the way I looked into this is I said, let's take the PMRKA that we used earlier, which is shown in blue, and let's compare it against the true scattering rate, or at least the truest estimation we have of the scattering rate using these full band Monte Carlo methods from Fermi's golden rule. Let's then assume that the difference between these two rates is purely attributed to the constant matrix element approximation, and therefore extract the energy dependence of the matrix elements from the difference. And we'll compare that extracted value against the average momentum exchanged, which is our blue curve here. And I think you'll agree that certainly close to the threshold, there's a remarkable agreement between these two curves. So the matrix elements are strongly dependent on the inverse square of the momentum exchanged. And that actually captures the functional behavior of the momentum dependence very, very well. So I took this approach and I applied it, and again in a high throughput framework, and looked at lots of different materials. I'm just going to show 4 materials here. You'll notice I show the same materials because unfortunately the literature is quite sparse in terms of comparable results. But certainly for aluminium nitride, gallium arsenide, silicon, and gallium nitride, the average momentum exchanged kind of fits the sort of trends that we would expect and gives us a good approximation for these matrix elements. What these plots show is the y-axis being the average momentum exchanged versus the initiating carrier's energy. And again, to make this computationally tractable, we can actually leverage all of the work we did way back in chapter 1. When we solved this minimization problem to find the threshold energy, we also have in our domain all of the states of the carriers that were involved in calculating that threshold. We also have an energy range over which this emin curve deviates. For every point in that curve, we know the momentum of the pre and post collision carriers. And so we can use this as an estimator of the average momentum exchanged close to the threshold, which is where these matrix elements matter the most. You'll notice that in the sort of high energy limits, most of these momentum curves kind of saturate to these sort of random values. Except for gallium nitride. It's a bit of a strange material. There's lots of interesting results there. Again, read my thesis. And so you can see in the dotted line here, I've got the average momentum exchanged as extracted from these minimization results compared to using sort of full Monte Carlo based integration methods. And I found that close to threshold, it really captured the dynamics that we cared about and was able to accurately correct that near threshold matrix element behavior. And so again, I felt satisfied, as did my examiners, that chapter 3 provided a computationally tractable method for extracting the momentum dependence of these matrix elements. And that brings me to the concluding remarks for this seminar. In chapter 1, in the first section, we investigated the thresholds of impact ionization, leveraging these fast global optimization methods to perform high throughput analyses. And we debunked the long-standing 3-to-2 band gap rule and identified candidate materials for avalanche photodetectors. In the second chapter of my work, I looked at these impact ionization probabilities and coined this new method, the probability moderated random K approximation, to correct that near threshold behavior of the onset of the scattering rate. The thing I was most excited about this work was this sort of new integration strategy using the marching cubes algorithm to solve these integrals, which involve the composition of a function with a direct delta. And there's a lot of applications for solving Fermi's golden rule and also for doing density of states calculations in general. And in the final chapter of my work, I looked at the matrix elements and improved the constant matrix element approximation by capturing its momentum dependence, and showed how we can use the results from the minimization problem, which is the most computationally efficient method presented here, to capture that near threshold behavior and provide a meaningful approximation to the total impact ionization scattering rate. And thanks everyone for your attention. I'd like to welcome any questions now.
Thanks, Ryan, for the nice talk. Do you have questions for Ryan?
Thank you, Ryan. That's a really clear presentation on something that I think can be made quite complicated. On slide 32, you had a nice comparison between the different.
Yes. Sorry.
Yeah,
This
this one.
Yes.
And so I suppose my eye's drawn to what's going on in gallium nitride,
Yeah, it's an interesting material.
because your silicon is fairly, stable. Gallium arsenide, similarly, and yet gallium nitride has this discontinuity, and I'm sure that relates to something in the band structure.
Absolutely.
Yeah, could you tell us a bit more about what's actually going on?
Yeah, so there is actually something special about these kind of saturating values, and it was something I picked up from this theory in mathematics called cube point picking or cube line picking. And so we often make the assumption that the random K approximation in the high energy limit is a good approximation because our initiating carriers and our post-collision carriers are uniformly distributed in K space. And that's true if the density of states continues to increase into this high energy limit. If we use a unit cube as our kind of basis set, then we can kind of get an estimator for how true this uniform distribution really is. And there's two kind of special numbers that pop out. On one of the previous slides, I showed this value here, 0.48. This is what happens if you have your initiating carriers perfectly uniformly distributed in a cube, and they are ionizing a carrier that lies at the gamma point, i.e. at momentum 0. So that's the average Euclidean distance between a random point in the cube and the origin. And it's called a Robbins constant, number 0, I think. And then you'll see this other value that they tend to saturate towards ends up very close to 0.6. I think it's 0.58 or something from memory. And this is another form of this constant if you have your initiating carriers randomly distributed and your post-collision carriers also randomly distributed. And this happens as you move to really high energies. Now your initiating carrier and your your post-collision carriers both lie in regions where the total density of states is really high. In gallium nitride, if we look at the band structure, that's not true. If you look at the density of states, it initially increases in the sort of conventional form that we expect. And then there's a range of energies in the conduction band where the density of states is very, very low. And we kind of pass that region twice. You'll see that we almost get to the first Robbins constant and then the second one, and then it drops away again. And that's because the initiating carriers cannot ionize any carriers where the density of states is low, and so they have to ionize much lower energy states. And so they need correspondingly higher energies, and so the average momentum exchange goes back to being almost a direct transition again. And so yeah, it's an interesting result, and it actually makes solving Fermi's golden rule for gallium nitride using these sort of four-band methods very computationally challenging, because a lot of the assumptions and approximations that you might make for the direct delta turn out to converge really poorly. And so a lot of the data I was able to extract from literature actually had quite poor outcomes for gallium nitride, particularly for electron-initiated processes. It's just a really challenging material. And I think there's lots of interesting implications for this in the way it's used in devices, particularly the sort of directional dependence of the electric field, for example.
Thanks, Ryan.
No worries.
Hi, Ryan. I'm François Ladrusa. I'm one of the co-supervisors of Ryan for his PhD thesis. This very clear talk reflects the good work that you've done throughout your PhD, and I commend you on the work that you've done. Personally, I'd like to say that Ryan was one of the best PhD students I had the chance to supervise over the 20 years at this university, so congratulations for that. At the beginning, you mentioned that there was an industry partner.
Yeah, absolutely.
Yeah, Silana, Norbert Krause. Would you like to say a few words about how your work fitted into their vision of what they wanted to accomplish during the PhD?
Yeah, absolutely. So, I mean, I guess the initial project was quite different to what we ended up executing, but throughout the PhD, we maintained this really positive working relationship with our industry partner. And we sort of utilized, the flexibility in the PhD to do some of the more exploratory work. And I think the initial goals were sort of to better understand how impact ionization works in wide and ultra-wide bandgap semiconductors. When Norbert was conducting his literature review, he found very poor models and very poor approximations for understanding this behavior, even in algan and GaN, which are the material systems that are conventionally used for these sorts of devices. And so I spent time visiting them and working with them on these models. And I think these insights were used to optimize the geometry of these UV LEDs. And, they have a working product that's now distributed into the world, and potentially one of the first commercially available deep ultraviolet impact ionization based LEDs, which is really exciting to be part of.
Thank you.
Yeah, thanks, Ryan. Amazing talk. Of course, here we are in the Center for Photovoltaic Engineering, and this sort of the idea of generating multiple carriers from a single photon in solar cells is this elusive goal. There's been some very small effects in silicon. So is there anything that emerges from your work that can be used to assess the probability of ever getting multiple carrier generation in silicon, or maybe to guide the material developments for a solar cell that could use that effect?
Yeah, I think so. Particularly these impact ionization scattering rates can be used to understand how the distribution function for the energy of carriers might evolve as a function of the applied electric field, and how you can engineer devices to potentially improve that high energy tail for, say, hot carrier solar cells. I think one of the other applications here is that impact ionization is intrinsically linked with its inverse process, Auger recombination, which is of very strong importance to solar cells. And these same methodologies can also be leveraged to extract the Auger recombination rates from first principles as well, which I think is an area for future work for sure. And I think that's quite exciting in the application of photovoltaics.
Yeah, that'd be interesting actually,
Yeah.
especially in silicon, where we have this extremely accurate modeling of Auger recombination. It would be interesting to see how your
to tackle the problem from first principles and see if we can meet in the middle. Yeah.
A separate question is on these aluminium gallium nitride LEDs, and you mentioned the problem with the P contacts. Has anyone ever tried, instead of building a conventional PN junction, at the moment there's a big trend in PV to go to heterojunctions, to build a heterojunction contact LED?
I think so. So, I mean, I got very quickly roped into the idea of studying impact ionization and less interested in the LED technology, but certainly in the literature review, there are novel approaches to doing this carrier injection, even some research on Schottky contacts, for example, which is sort of seems quite out there. You wouldn't expect them to be very good. That being said, commercially at least, algan is really still the go-to material. I mean, it offers the flexibility to tune the band gap anywhere from sort of 4 electron volts up to 6, so you can really tune your wavelength, and it's a well understood material system. But I do think these complementary technologies are being investigated at universities across the world at the same time.
No more question? If yes, we thank Ryan and Garen for the nice talk. Thank you.